Hi, in this video I would like to show you how I designed and built this constant current electronic load. Electronic loads are widely used to test and characterize certain power supplies, batteries, power banks, laptop power supplies, and so on. What I would like to achieve building this device is to reuse parts I already have. I only need a constant current electronic load, so that's what I'm going to build, and it is going to be analog only. For the maximum voltage and current, I was thinking about 20 volts and 10 amps, and the maximum power about 50 watts. I think that's achievable in this package. And I would like it to be self-powered, so having an internal battery, which is also rechargeable. Okay, so let's start with the parts I already have. First of all, this needs a box. I have this plastic ABS box from years ago. I would like to have some sort of display. This is just a basic volt and amps measuring module, couple of MOSFETs, obviously, battery holder, and 18650 lithium cell. For that, I'm going to need some sort of charge controller. Of course, the battery voltage will be too low to drive all these, so I need some sort of step-up converter, which is just another module. For setting the load current, I was thinking of a coarse and fine potentiometer, classic solution, so these two. I'm going to have to need some sort of heatsink for the MOSFETs. I have a couple of heatsinks from motherboards and other devices, and of course a fan to blow air across these heatsinks. And the brain of this device is an old circuit I've used for a couple of years. This was a dummy load, and I would like to reuse this circuit. Lastly, I need to connect this load to a power supply or a battery, and I have these two banana plugs terminals. Okay, let's look at the circuit diagram. I'm going to start with explaining the main board, which was kept the original main board, except I added some labels on the outputs and inputs. I added these power distribution connectors, and otherwise it's the original board. The next important part of this build is setting up the load current, and I chose the classical method of having two potentiometers, one to control coarse current and one to control fine current. And I only had two potentiometers of the same value. So I thought about maybe I could order a 1K potentiometer, but I wanted to solve this using two potentiometers of the same value. So I decided to use this sort of overkill circuit with two op-amps. Each of them forms a unity gain circuit, and there's a summing point across these resistors, and these resistors have different values. So one of the potentiometers will have a larger impact of the sum value. And I have a simple 100K trim potentiometer on the output just to set the maximum voltage. The next part is power dissipation, which is accomplished by two parallel MOSFETs. I chose two MOSFETs to hopefully share the load. This heatsink might not be large enough to dissipate the power I would like to put into this device, but we'll see. The last circuit on this diagram is the input protection. I thought about what kind of input protection I would like to incorporate into this build, and I know about the MOSFET reverse polarity protection, but I chose a different approach because I would like to test very low voltages as well, and I would have to get a MOSFET which has a gate threshold voltage of a couple of volts, and my lowest goes to maybe 3 to 5 volts, which is, I think, not low enough. So I went with this, I think it's called a crowbar circuit. Basically, if a reverse polarity voltage is applied, then the diodes short the input and the fuse blows. So it is a destructive protection mechanism, but I'm not expecting frequent reverse polarities applied to this device since I'm the only one who's going to use it. I could include overvoltage and maximum power protection, but I don't think it's necessary for this design. Down here I have a simplified block diagram. The battery goes into the charge control and protection circuit, then it goes to the main switch. I thought about putting the main switch between the battery and the charge controller, but that would mean you can only charge this device if it's switched on, which is, I think, not the best solution. So you should be able to charge it while it's switched off. Next, it goes into the DC-DC converter, which steps up the voltage from the battery's 3 to 4 volts to 12 volts. This is very interesting. Why is there an isolated DC-DC converter here? Well, because it turns out the volts and amps display I'm trying to use must have a separate power supply to power the entire display, separate from the measured current, basically. I thought about maybe adding a small button cell to power this, but then I would have to charge that cell or replace it occasionally. So I thought I would use this small isolated DC-DC converter. I think it can output 200 milliamps, which is more than enough to power this. Okay, let's start assembling everything. As you can see, I've already drilled and cut some holes and placed some of the modules and devices. I determined the location of components by just trial and error. I know, not very scientific, but it did work. I used a combination of hot glue and double-sided sticky tape to stick down the components which remain cool, and I used some other method of mounting for components that do get hot. Okay, so I think it's almost completely assembled. The wiring is not the best, could be better, but I don't care. Let's test it. The heatsink is not completely installed, so I'm just going to hold it. So will this go up in smokes and flames? So far so good. Let's try to turn it on. And it does work. You might be wondering why I left the input protection out. Well, because I kind of forgot about it, but I'll install it now. So this will be the finished device. I mounted the heatsink using these perforated strips in a way that it doesn't touch the plastic housing anywhere. And I had to drill some holes and use some screws to mount it to the case. But there's just one slight problem with that. The heatsink is directly tied to the middle pin, which in this case is the drain. And since the drain is connected to the positive input, these screws are directly connected to the positive input, which is not very safe. So I printed a couple of these half spheres, I guess. I'll glue these on later. By the way, these caps turn out great, and you can see a slight pattern, which I believe is caused by the stepper motor on the extruder, but it gives it a nice finish, I think, and on the inside as well. The voltage measurement is slightly off, or maybe the power supply's measuring unit is slightly off, doesn't really matter. Okay, so I've been running it for a couple of minutes now with the lid on because that provides the maximum airflow and that's the operating conditions it will work in. So let's check the temperature of the heatsink. I have my infrared thermometer. Shows about 55 degrees C. Let's try to up the current. Well, this power supply can do, what is that, 45 watts maximum? So I guess that's the maximum we'll be testing it at. So at 45 watts, the temperature went up to about 70 C, and I started to smell a sort of electronic smell. So I think about 30 watts, which is less what I hoped for. I might redesign some parts in the future, but so far I'm happy with this device. Okay, thanks for watching.